presentation is on the effects of viscosity on the average rate of diffusion. Hi everybody, recently we completed a computational experiment on diffusion. While this was a very useful way of visualizing diffusion, the simulation was not an accurate representation of the actual physics of diffusion in real life because it assumed that all the collisions were perfectly elastic, meaning kinetic energy is conserved. In order to show what actually occurs in a real-life situation, we conducted an experiment looking at the velocities of micro-sized beads in two different mediums with two different viscosities, that is, water and soap. Beforehand, we assumed that the soap had a higher viscosity than the water. Our graphs demonstrate an overall decrease in velocity over time, indicating the presence of non-elastic collisions. Since viscosity refers to the friction between molecules of fluid, we hypothesized that the beads that were placed in the more viscous solution would have moved slower due to the greater loss of kinetic energy associated with the greater friction. However, our results did not support our hypothesis, and instead the beads that were placed in the soap had a greater velocity. So the first thing we should address is the concept of diffusion. Diffusion simply refers to the movement of particles from an area of high concentration to an area of low concentration. Further, while both the computational model and the experimental model focus on the diffusion of molecules, the biggest difference was that the computational model assumed that all the collisions were perfectly elastic, as demonstrated by the line of code saying particle dot velocity z equals negative particle dot velocity z. This does not necessarily hold true for a real-life system.
All right, so our first objective during our experimental design was to show the differences in rates of diffusion between the two mediums, water and soap. Assuming soap would be more viscous, we used 4 polystyrene beads in each, then analyzed them in the tracker software. Our second objective was to show that the collisions were inelastic in real life. First, we ran a model that was a simulation of beads in water. This was in a perfect world, so no energy is lost. Then we had a real-life model. In this, energy is lost as the beads slow down and stop. Momentum is transferred from the beads to the water and then back to the beads. These graphs are the displacement of beads. As you can see, the beads in soap moved further than the beads in water in the same amount of time. The graphs for velocity are now on screen. In the real-life model, kinetic energy is lost. The general trend of velocity is decreasing, thus, and the equation for kinetic energy is k equals 1/2 mv squared. So as velocity decreases, so does energy.
So let's talk about the connections to physical concepts. In the real-life experimental model, the collisions are not elastic, they are inelastic, so not all kinetic energy is conserved in the collision due to internal friction. Therefore, more viscous collisions leads to more internal friction / inelastic collisions, which results in the molecules moving slower. However, momentum is conserved, transferred through the collisions. Since mass and momentum is and must be conserved in this situation, if kinetic energy decreases, then velocity must also decrease. The results we got from the experiment, the general velocity of beads in soap is greater than that of the beads in water. This does not support our initial hypothesis though. However, as said before, the graphs show a general trend of decreasing velocities, which indicate decreasing kinetic energy in the system and being transferred to internal energy. Possible explanations for these results include only 2 mediums. We only tested 2 mediums. The differences in viscosities were not large enough for sufficient results, and the soap molecules have a much greater mass than water molecules, which results in greater change in momentum to the beads, which results in greater velocity into the beads.
During our experiment, we faced some limitations and errors. An error was the way in which we placed our solutions onto the slides. If the pipette was angled, the velocity would be much greater than it would have been straight on. We also started the video before placing the solution onto the slides, so the velocity of the beads was bigger at the beginning of the video. Some limitations we faced included that there were only 2 solutions that we could test when we thought there were 3. This limited the variation in data we could have achieved. Another limitation we noticed was that some of the beads in the water solution moved in the negative direction, which would give us a negative velocity. There was also the limitation of not being able to see movement in the z direction since the bead moved in 3D. Some conclusions we made were the average velocity of the beads in the water was less than the average velocity of beads in soap. However, these results are not a good representation of the study because we only had 2 different mediums to test. Our results could be more accurate if we tested other mediums such as oil, honey, or cornstarch. This way we would have more varied data. We were also able to conclude that the collisions of the beads in the solutions were inelastic, considering that they lost velocity over time, showing that kinetic energy was not conserved within the system.